kick off this conference by talking to you about this sort of rather counterintuitive thing, which is sort of this tension that I think exists between expressive power on one hand and analytical power on the other hand. And as you sort of expand one of those things, you necessarily contract the other. So as a wee young Runar, I was programming in Delphi on Windows. Anybody, any Delphi programmers in here? Yeah. All right. So why Object Pascal didn't take over the world, I will never know. But so yeah, I was programming in Delphi on Windows, and I was working for a publisher of poetry, of all things, and this was the first program I ever sold to anybody. And so one of the things that this thing needed to do was to print out sales reports for the publisher, and it needed to do that on this beautiful piece of machinery right here. Now, unfortunately, at that time, Delphi did not have very good facilities for printing. So I did what any hacker would do. I got out the star.matrix printer reference manual, and I just took their SQL tables and I turned it directly into printer control codes over the parallel port. Now, of course, once you've printed something on the paper, it's on the paper and there's nothing you can do. So then the client comes back and says, hey, these reports look great, but I got a new printer, so can I print this out on my new printer? And I had to say no. And then they asked, well, I'd like to take this report over here and this other report over here, and then sort of put them together side by side on one sheet of paper. Can you do that? And I had to say no. But going directly to the sort of full power of the printer control code by having complete control over the printer, I wasn't making use of any kind of abstraction that would allow me to sort of abstract over the printing. So what I should have been doing was to generate some kind of intermediate form that allows for composition, some kind of syntax tree or something that I could then go and render out to the printer as sort of the last possible step. So at some other point, I was working with strings that rather look like this. So some strings that contain some SQL, right? So it's select some stuff from some table where some condition is true. Now the problem with this is that it's a string, right? So the structure of the SQL in here is sort of lost inside of this string. So if you want to do something like add a column or add a condition or something, that's actually really difficult to do because you have to sort of rediscover what it is that the structure of the string actually is. Or you have to do some horrible hack, which I've done a lot of. So again, what I needed here was an abstract representation, some kind of intermediate form that I can then manipulate. And then at the last possible moment, when I'm really sure that I don't want to manipulate it any further, I compile that to a string, and then I send that to the database, right? So maybe sort of what I was discovering was this principle that any problem can be solved by just adding another layer of indirection. And so David Wheeler here is a little bit tongue-in-cheek about this, but he makes a good point about abstraction and composition. So as an illustration, when we're working with explosions, as you do, you want to work with a representation like this, right? So you want to work with the unexploded form, right? You want to, well, because it's compositional for one thing. Like you can take two blocks of TNT in Minecraft, and you can put them together, right, to make a larger explosion. And then, just like when we're working with side effects in our programs, we want to work with them also in this sort of unexploded form. We do not want to work with them in this form, right? So whenever I see side effects in code, this is what I think of. I just think of big explosions going off everywhere. So yeah, once you've sort of detonated your dynamite or your side effect, composition is out the window. And when we're working with explosives, we really want that extra level of indirection. So I think that this is a mistake that a lot of people make. I know that I make this mistake a lot, and it's a mistake that's really easy to make, which is choosing to work in a language that is sort of too large for the task at hand. It's insufficiently abstract and insufficiently precise. And so we tend to optimize for the task at hand, for the thing that we're working on right now, and forget to optimize for the task that's down the line, which is integrating our code into a larger system or a larger conceptual framework. So going to a concrete representation of what we're working on sort of too early. And this comes up in all kinds of situations, and not just with side effects. For example, in this very simple geometry problem, let's say we want to find the area of the yellow square, right? Really simple. We know that this red triangle is a right triangle, and we know the two sides, that they're both 2. So, we know our Pythagoras, and we just say, like, well, 2 squared plus 2 squared is 8, and then we take the square root of 8, and we get something like 2.828 something, right? And we, obviously turn that into a double, and then we square that, right? So when we square that, we end up with something like 8, so not exactly 8. So what has happened here is that we've sort of detonated our square root too early. We've lost precision. We've gone to a representation that is sort of insufficiently precise, and it doesn't allow for this kind of compositional reasoning, right? So we've sort of created, when we take the square root and go to doubles, we've created this barrier that disallows further composition. And something has been lost here, more than just the sort of precision of the answer. What has been lost is the algebraic relationship between these squares, because the Pythagorean theorem is really about the relationship between 3 squares that all lie on a triangle like this. And the relationship is that, the area of the square that's on the hypotenuse is the sum of the areas of the other 2 squares. Right, so hopefully you can see the analogy here between this and side effects. So using side effects is like working with, distances and doubles, and using algebraic data types and pure functions is rather like working with, the algebraic relationships between squares. So the moral of the story in this case is that you want to work symbolically, right? You want to manipulate symbols for as long as you can, and then sort of detonate to decimals or to some kind of representation that is larger, or sort of that could mean more possible things as the last possible step. So yeah, this kind of problem of having concretized too early comes up in situations that are much closer to our hearts, right, as Scala programmers. For example, the problem of binary compatibility. So binary compatibility comes up because of this kind of problem of having gone to a binary representation sort of too early. So when the Scala compiler goes and generates a binary from a Scala file, it creates this intermediate form, this kind of tree, like the syntax tree of the Scala. And then it goes and throws that away, right? And just leaves the binary for you to then consume to construct further code, right? So then you write some more code, and that consumes the library that you had just compiled before. But now what you're consuming is a binary, and the binary representation is sort of strictly larger and less precise than what you want, right? So we've sort of done the same thing as when we took the square root and went to doubles. We have thrown away this abstract relationship between entities in Scala. And so then when we try to combine that with other things, what we're thinking about is combining trees. But what we're doing actually is trying to recover sort of hypothetically the idea of the tree from the binary, which may or may not represent that actual tree, because we may have done things like, gone to a different version of that library or gone to a different version of Scala C altogether. A partial solution to this that Martin Odersky and others are working on is this idea of shipping the abstract syntax tree along with the bytecode. So, and they're calling this tasty trees, which I think is kind of an awesome name. And so, yeah, the reason here is that, you know, the bytecode representation is sort of too large, and it's a barrier to composition and reasoning. And so not throwing away that abstract representation helps, or is going to help enormously, I think. So the moral of the story here is that, you know, we want to work with syntax trees for as long as we can. We want to work symbolically, and then we want to go to binaries as late as possible. We want to compile as the last possible step. Because really, compilation, when you really think about it, is an optimization step. Like, you really only need to do it when you want the thing, you know, to run quickly on the machine. And as we know, premature optimization is the root of all evil. But more than that, I want to say that that's really just a special case of something else. That the root of at least sort of a moderate amount of evil is premature loss of precision, or compilation, or folding, or going too early to a too concrete or too large representation. So to a representation that is sort of too unconstrained and too powerful, right? And this is sort of a classic mistake, or a classic error, I think, that is really easy to make. And it's not just something that beginners do. I think experts make this mistake all the time. For example, if you open up any calculus text, you'll see that they go directly for the most powerful number system they could possibly think of, like everything that could possibly have everything that they might possibly need, right? And it's easy to think, I mean, it's interesting to think about what kind of structure we're missing out on, what kind of reasoning we could possibly be doing sort of within calculus if we, you know, restricted ourselves to maybe something slightly smaller than a number system that includes, you know, uncountable reals and non-computable numbers and things like that. And I want to say that this is sort of the same phenomenon as doing like stringly type programming, where, you know, like with the SQL, where, you know, I have just a string that represents whatever I'm working on, because you can always represent anything as a string, right? So why not just work with strings? Well, because, you know, then you have to rediscover what is the structure of the string. And I want to say that reaching too early for things like general recursion and reaching for languages that have side effects are also a species of this same kind of thing. So, because, you know, when we're doing these things, when we're coding, you know, we should ask ourselves, like, do we really need general recursion? Do we really need to go to a string here? Do I really need a side effect here? And what am I missing out on? Well, the fact is that the more expressive some language can be, the sort of larger it is, the less we can analyze what we have expressed in that language. Because the more kinds of things something could potentially be, the less we can actually reason about what it is, like what it actually is, right? So, you know, as the potential stuff gets larger, this sort of number of things that we could actually sort of predict about it is smaller. So my point is here that we want to choose representations that are sufficiently abstract or, you know, sufficiently indirect, because abstraction buys you this compositionality, and failing to be abstract enough creates this barrier. So you detonate sort of too early. But abstraction also buys you precision. And now many people might think that abstraction and precision are opposites, but they're not. In fact, I want to say that abstraction is what makes precision possible. In the words of Edgar Dijkstra, the purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise. And to demonstrate that in a very simple way, here is a signature that is not very abstract. If you ask yourself, how many implementations exist of this type? Like a lot, right? It's something like 4 billion to the 4 billionth power. And you know, that's a huge number. And that's not even counting the ways that you could do side effects and throw exceptions and, you know, involve nulls and absurdities and things like that in a program that meets this type signature. But if we allow the type to vary, that is, if we abstract over the type, so this type signature, you know, is sort of the same as before, that it's, you know, it's a function from one type to another, except now the type has been abstracted out. So now how many implementations exist for this signature? One, right? Well, there's only one that actually, you know, makes sense, you know, without side effects and without nulls. And so if we don't appeal to those kinds of things. But there's only one way that you could take a value of type A for any type A and then return a value of type A for that same type A. You have to return the value that you were given, right? So here, in allowing the type to vary, we've introduced a freedom to the caller, yeah? So they can choose any type. But this freedom constrains the implementation, yeah? And that, in turn, introduces a precision because this type specifies precisely what this function is. And this is very sort of counterintuitive that, you know, making something more abstract is making it more precise. That, you know, making something freely vary then creates a constraint. But I want to say that sort of in general, that you know, if you introduce a freedom at one level, then that leads to restriction sort of further down the line at a different level. And this works the other way around, that if you constrain something sort of upstream, then that leads to freedom and power further down the line, because now you can, you know, once something is very constrained, you can now reason more about what that could possibly be. Okay, so let's take some examples. For example, monads versus applicatives. To give you a quick sort of refresher on monads and applicatives, so a functor is just something that you can map over, right? It's some data type f for which there exists a map. Right? So if you have a function from A to B, you can get a function from f of A to f of B for this data type f. For example, if f is a list, then, you know, you can map over the list with a function that takes that changes the elements to some other type. All right. Now, applicative functors are functors that you can map over, but they come with these additional capabilities. The capability that you can take any value and sort of put it inside of the context. For example, you can, with a list, you can take an element and you can put it inside of a single element list. And then the other capability of applicative functors is that if you have two of them, if you have an f of A and an f of B sort of side by side, you can put them together. And you can do so only if you have a function where you can combine the elements, right? The A's and B's in those two f of A and f of B. If you can combine them into C's, then you can combine the f of A and f of B into a combined f of C. All right? So you can sort of sum them, yeah? Or multiply them. And then an applicative functor that comes with one additional capability is a monad. So a monad is an applicative functor that has this additional method join, where we can, if we have a nested f, like if we have an f of A, then we can turn that into an f of A. For example, I'm going to go on with the lists. If you have a nested list of lists, then you can concatenate all those lists into a single list. If you have, you know, a tree with trees, you can graft all the trees into the nodes of the tree, and you have a sort of a flatter tree. If you have an option of option, you know, you can collapse those things together, right? And this allows us to do, you know, it allows us to write flat map. So flat map is map then join. And then, you know, it allows us to use for comprehensions. And so it allows us to assign to variables and then use those variables later on in our sort of nested, in the inner context. But in doing so, something is lost. When we go from applicative functors to monads, we gain this additional capability of joining and flat mapping, but we lose something as well. we lose the ability to mechanically compose these things. So if you have sort of two data types or two languages or two applicative functors, F and G, you can always mechanically compose them into a composite functor FG. So for example, if you have a list of options, you can map over both of those structures at the same time, and you can combine two maps of options or lists of options or whatever and combine them together using the applicative. And coming up with an applicative instance for the composite is completely mechanical and can be done once and for all. And the implementation is really, really simple. Right? It's just like, for the pure thing, just lift the pure thing and, or literally just compose the pures. And with map 2, it's literally just compose the two map 2s. All right? But if we want to do this with monads, this is not possible in a mechanical way. Composition of monads requires a mechanism that is specific to the monads that are being composed. So we need to know something extra. We need some additional information about the individual monads in order to be able to compose them. And this is why we need things like monad transformers. I want to say that this applies to monads that you want to compose in this particular way. You may be able to, you can use things like coproducts and other things to compose monads in other ways. But if you want to, if you have two monads, F and G, and you want the monad FG, then you may be able to get it, but you cannot get it in a completely mechanical, once and for all way. All right? So this is an example of where something is strictly more powerful than another thing, but then is less compositional, right? We lose some kind of composition. So monads offer more for the first order. Like we can take a monad and we can immediately do more stuff. But a monad can participate in fewer applications, right? It can participate in fewer compositions of things. Yeah? So it can participate in fewer systems of solutions, if you will. So again, this is an example where a constraint at one level, we constrain ourselves to applicative functors, and this creates a freedom or power at a higher level, at the level of composing systems. All right, another example of this is actors versus futures. And I kind of wanted to put in a little parentheses like fight, right? So futures are more constrained than actors, in the sense that they have an algebra. So you can do sort of algebraic reasoning with futures. So for example, if you have something like a monadic future, you can do things like fork. You can take an A, you can create a future A. You can map. So if you have a function from A to B and you have a future of A, you can extend that future just by sort of appending that function and say, hey, once you're done with this, do this other thing as well. And then you can join. That is, you can tell if you have a process that spawns some subprocesses, you can ask that process to sort of wait on its child processes. And this all sort of behaves according to the monad laws, and so that fact gives us the power to use this with monadic libraries and to reason about it as a monad, right? And so that gives us this algebraic reasoning. Now contrast that to a type like this, right? So this is the type that actors are, in Akka at least, are built around. So this is a function from any to unit. And so this is completely unconstrained, right? So you start with, anything. Right? You could receive a value of any type whatsoever. You don't know upfront what this could be, and then it just returns a unit. And even that is not really true. What it does is not return a unit. It actually goes and has a side effect, right? So it'll, the type of this is even bigger than this, right? So there's no algebraic theory about this type, right? There's no way we can sort of reason about this algebraically. And this is aggravated by the fact that not only can the actor can the actor be anything, like, the thing that's behind the signature any to unit could be anything, it can become something else, like between calls to the function, right? So if somebody has called become and unbecome, like between two calls of your function, it could be doing strictly different things. So I was given a talk at one point about Scala concurrency, and somebody said, well, why would you not want to do this, right? Well, if I can have this power, obviously, Akka actors are more powerful than futures. Why would I ever want to use futures? Because I can do strictly more with Akka actors. Well, precisely because you can do more with Akka actors, you should want to rather use futures, because they're more constrained, and because they're very unconstrained, that makes Akka actors hard to reason about, right? So not only can it be anything at all, it can become something else between calls. So to take an extreme example, or sort of Akka actors are sort of the extreme example, right? They're really, really powerful, right? You can do, it's unconstrained side effects, right? You can do anything you want when somebody calls your actor. But precisely because they're so powerful, our reasoning about programs is severely limited, right? Because, like the Right Honorable John Dahlberg Lord Acton once said, power tends to corrupt, and absolute power corrupts absolutely. Now, he was obviously talking about political power, but in the case of side effects, what is corrupted is our ability to analyze and compose. For example, if you consider this simple kind of equation, right? So I'm going to stop picking on actors for now. But if you consider this kind of equation where we want to say that, if you have a list called x's, and you map over that by subtracting some number n, and then you map over it again, and you want to add another number n, shouldn't that be the same list that you started with? Yeah? Makes sense? But what if n has a side effect? Right? So if n has a side effect, then this is clearly not going to be the same, right? N could throw an exception. It could be null. So x's could actually just be, a list, and then, this other expression could be throwing a null pointer exception. So in the presence of exceptions and side effects and general recursion, we don't actually know this to be true. Like, we don't know that mapping over a list twice and sort of doing inverses, or something that should obviously work, we don't know that it does. But if we restrict ourselves to total pure functions, we actually can do this sort of reasoning. All right? So this is an example of where a constraint at one level affords us improved reasoning at a higher level. So don't want to pick on actors and side effects too much. I have sort of a larger point. But the cost of side effects, which is just one of these examples, is that we lose the ability to reason in this way. We lose, compositionality. We lose the ability to reason modularly about concurrency and about parametricity and other things like that, right? So our programs can do strictly more things if we have side effects, but we can conclude strictly fewer things about them. All right, so let's go now to another example of this principle outside of programming. So enough about side effects. I want to talk about where this comes up in information security. So in information security, there's this principle called the principle of least privilege, which states that a user, a program, or component should have exactly as much authority as necessary, but no more. Right? So why no more? Well, because if you minimize the privileges that a particular component can have, then you maximize the ability of composing that component with other things, right? Because a composite system requires the largest privileges of all of its components. It requires the max, right? So if you have a composite component, you just find the one that needs the most privileges. The sum of all the privileges is what is required by the composite. But the fewer the privileges a component needs, the easier it is to deploy in a large environment. And then modularity is maximized as well by minimizing privileges, because we know that the interaction of that component is limited, and we can reason sort of mechanically about where that interaction actually happens. And so we have overall sort of better guarantees about system stability, and it's also easier to test our limited components in isolation. Right, so another example of where the more a system can do, the less we can predict what it will do. Yeah? And this kind of relationship, right, it comes up in all kinds of things. For example, with applicatives and monads, with side effects versus, algebraic reasoning, and in context-free versus regular grammars. For example, if we have two regular grammars, we can mechanically check whether they are equal. We can check whether they describe the same set of strings. But if we go to context-free grammars, which are strictly more powerful, we cannot conclude this. Right? There's no known algorithm that will tell us whether two concrete context-free grammars are in general the same. Euclidean versus Cartesian geometry, right? So if you start with Euclidean geometry, like all space is isotropic, right? All the directions are the same. Space is the same everywhere. All the dimensions are compatible. All curves, if they look like they intersect, they actually do. But if we constrain ourselves to coordinates, if we constrain ourselves, to the sort of Cartesian plane, then we gain algebraic reasoning. We gain the ability to reason about geometry algebraically, and we can reach for things like linear algebra and category theory and other things to inform our reasoning. So an example of where a constraint creates a freedom or a power. And things like roadways, the fact that you can't just drive, or the fact that you choose not to drive, from your hotel directly to the conference venue, just over the hills, right? And you drive on the road, it gets you to the conference more safely and more quickly. And it's compositional because you can get a lot more people. You can get a whole bunch of people very safely along the road and very quickly. And things like commodity components, like if you have if you're building some kind of service and you want to be able to reason about you want to buy a Linux server that has these specific sets of components, and so they're all interchangeable. The system is compositional. It's like go into your wardrobe and you only have one set of clothes, lots of instances of the same set of clothes. You can reason compositionally about your wardrobe, and you never have to worry. When you get up in the morning, it's oh, what should I wear, right? You just put something on, and you don't have to worry about it. And other things like putting together Legos, they fit together in a very obvious way, rather than building something out of actual concrete and steel, and Tony Hawk Pro Skater versus actual skateboarding, and things like that. Obviously, Tony Hawk Pro Skater is easier to do than actual skateboarding because you're sort of on rails, right? So all of these things have in common that a restriction at one semantic level translates to freedom and power at another semantic level, right? So if you make something maximally general for the first order application, you reach for the most power that you can when you're building, the immediate thing, then you minimize your possibilities for composition and for reasoning about higher order applications. And it's important not to go too powerful too quickly, because if you constrain yourself to a small language, you can always embed that language in a larger one later on, right? You can always take your small language and then just translate it to a larger one that fits both what you were saying and also a whole bunch of other stuff that you might want to say in the future. But this does not work the other way around, right? You cannot take a large abstraction and sort of fit it into a smaller one, right? When you do that, you get what people call a leaky abstraction, right? There's strictly more stuff that you need to be able to say than you can fit in the language that you're actually using, right? I mean, it's like when you detonate your dynamite, right? It's really difficult to then take the explosion and sort of put it back in, yeah. it might take a while. So another way of putting this is that the more capable your syntax is, the fewer sort of logical semantics you might be able to choose for that syntax. In the words of William Lauvier, syntax and semantics are a joint, right? So what does that mean? What does it mean for syntax and semantics to be a joint? Well, it means something very similar to what we've just been talking about. So let's do a little game where let's consider a category C of all the concrete things in this room, or actually of groupings of concrete things in this room, right? So for example, an element in the category C might be like those 2 seats over there, or Dean and Miles and one other person or something, right? So so these are concrete groupings of things. This is the category C, and we want to say that there's a partial order for this, for this category. That is, there's an arrow from A to B when B is a subset of A, right? So when B is a smaller, or is contained in the grouping A, for example, those 2 seats over there are contained in the group of all the seats, right? And then we have this other category, which is ways of describing those things. For example, we might say like seat or chair or something, and that would be a way of describing some objects in this room, or people, right? That might be another way of describing some objects in this room. Yeah, and then we have a partial order for this category as well. That is, we want to say that there's an arrow from A to B, from the concept or the description A to the description B, when B is a more specific description than A. For example, if we have something like thing, or let's say furniture, and then that is strictly larger, a less specific thing than saying like, auditorium seat, right? Okay, simple enough. So now we have a functor from C to D, which is a mapping that takes a concrete group of things in this room and then finds the most specific description in our arsenal that fits that group of concrete things, right? So for example, if we have those 2 seats over there, we might want to map that to like a most specific description, which might be seat, or we might have something like red seat, right? It depends on what our descriptions contain. But the important thing is that F will find the most specific description that we have available for that group of concrete things. And then there's a functor that goes the other way, which given a description D, or a description in D, it will find the most generous group, or the most capable group of elements that all match that description, right? So for example, if I say seat and then I apply G to that, I want to get like all the seats in here, yeah? So you might say that G or F will create a generalization for something, and then G will forget that generalization and go to the canonical example of that generalization. So this obeys this kind of relationship where if we have some grouping A, some group of concrete things A, and then we find the best available description of that grouping, so that would be F of A, and then we want to go back to concretes, we will end up as something that may be larger. That is, the best available description of some concrete group may apply to a larger concrete thing, right? So for example, those 2 seats over there, I might go to seat, but then when I go back from seat to the room, I will get all the seats, right? So that's the lower one. And the upper one goes the other way, where if I get the most generous group described by some concept, B, that group may in fact be described by a more specific, there may be a better fit for describing that, right? that that concrete grouping. Okay? So there's this sort of relationship that goes in both ways. So the important thing here is that as we go from smaller concrete groupings to larger ones, we get strictly more objects, right? That is, the set is more capable. Yeah, so, but the number of possible characterizations of that set gets smaller. That is, we can sort of reason less about that set. Where the most specific characterization will actually get less specific as we grow the set of concrete things that we want to describe, right? So, for example, like a group of 2 seats, that might be best characterized as seat, right? But if we go from a group of 2 seats to 2 seats and miles, that group is more capable, right? Like 2 seats and miles are more capable than just 2 seats. We would like to think, anyway. So we can do strictly more things with those, right? But they're harder to summarize, right? Because what do miles and 2 seats have in common, right? That might be difficult to come up with sort of a very precise generalization of that, right? And also, if we find some generalization and then we go back to the room, we may not find miles and 2 seats again. We may find a group that is much, much larger than that, because that concept will apply to a number of other things. Yeah. So this kind of thing, this kind of relationship, is called a Galois connection, after Évariste Galois, a French mathematician, and it's a specific kind of a junction. Now we were talking about how syntax and semantics are a joint. So you can see that these 2 categories, C and D, right, where we have maps between them, they're sort of mirror images of each other in a sense. So there's a one-to-one correspondence between 2 partial orders in a very precise sense. And the sort of relationship that we can, what the relationship that we were describing previously, what it sort of means, is that the most efficient description of any concrete group A will be less specific than any description B, precisely when, this is that green thing, so precisely when A is smaller than the largest grouping described by B, right? So we can go, so instead of considering just functors between categories of sets of objects and descriptions, we can generalize this to any category. And since we can generalize to any category, let's just pick the Scala category, right? So we can say the same kind of thing about junctions in Scala, right? So F and G are then just ordinary Scala functors, and then there's a one-to-one correspondence between these arrows, right? If you could go from F of A to B, then you can go from A to G of B, and vice versa, right? So, that's all very sort of abstract, but let's see that in Scala code. So we can write a trait like this, a junction, where we can give an example of an adjunction between 2 Scala functors. So F and G are functors. And then we can say that, well, we have to implement 2 methods. One of them takes arrows from F of A to B and gives you an arrow from A to G of B, and the other one goes the other way. That is, it takes arrows from A to G of B and it gives you F of A to B. Yeah? And the sort of canonical example of this in Scala is the adjunction between sort of the tuple functor and the reader functor. Right, so, between producers and consumers, you could say. So here, you could see that this adjunction is witnessed by currying and uncurrying, right? So F, in the abstract, is now in the concrete a pair with R, right? And G is now in the concrete a function that receives R, right? So then we can show that this relationship holds, because if we have an arrow from A and R to B, then we can construct an arrow from A to R to B, right? And that is just currying. And then if we can go the other way, and that is just uncurrying, yeah? So what I want to draw your attention to is that these two types, pair with R and function with R, they sort of fit together, right? You can feed one from the other. And as the producer, the pair, becomes more capable, the corresponding consumer has to become more capable as well, yeah? So a freedom in the producer becomes a constraint on the consumer. And if we make the producer less capable, it becomes compatible with strictly more consumers. That is, a constraint becomes a freedom. And this is important because most software that we write are consumers. Most of the software that well, at least I hope that most of the software that we write is going to be integrating some systems. It's going to be abstracting over something that has been, some kind of concrete stuff or something, right? So most software that we write is going to consume some things. So most of the software we write, we have not yet written, and we're going to consume the software we're writing today in that software. So it's very important, I think, to constrain for the first order application to allow ourselves a freedom and power at the higher order. And so yeah, we could tie this into variance, right? So the tuple type has R in the covariant position, but then it's in the contravariant position in the function type, right? So as R grows in one, it contracts in the other. Okay? So the other sort of canonical adjunction we can talk about is the adjunction between free and forgetful functors. So free as in free monads and free monoids. So list is a free monoid. And that adjunction, if we take list, for example, that adjunction is witnessed by the fact, so the left side of the adjunction, the free side, is witnessed by the constructors of the list data type. And the other side is witnessed by fold left and fold right. Right? So it's saying that there is an adjunction really between data types and then between the constructors of the data type and then the algebras that we can use to deconstruct those data types, right? So the producers of the thing, of the data, and the consumers of the data. Yeah? So I want to summarize here and say that when we're writing software, we want to reach for the least powerful and most precise abstraction that we can, the thing that will allow us to say exactly what we mean and no more. And then, we want to sort of build that, and then we want to detonate that as late as possible and turn it into a sort of more powerful, larger language, and sort of let it escape, right, at the last possible moment. Because once it's out, we can't put it back in, right? We're now in a larger language. And I want to say that this kind of premature loss of precision or loss of abstraction is the root of all evil in the Donald Knuth sense. That it creates a lot of problems for us down the line that we then have to go and fix. Like it's a creator of technical debt. So yeah, a constraint at one level leads to freedom and power at another level, and for that reason, we want to plan ahead. When we're building something, we want to know that we are going to want to integrate this into a larger system. So plan for that. Plan for algebraic properties and compositionality. And don't always just reach for the most expressive thing that you could, the thing that will do everything that you might possibly need, because then you might paint yourself into a corner. And that's all I have. Thank you. Now, do I have time for questions?
Yeah, one.
One, okay.
And then I'd like to make a little announcement.
Okay. What is the question?
Can you just shout it out because we haven't prepared this?
Oh. Boo.
We may have to abandon this already because some people have said the Wi-Fi is not consistent enough for everyone to have access.
Okay.
Has anyone else found that?
Yeah.
Okay. So in future shout-out questions, if speakers can repeat the question, that's good for the video.
Okay. Only one question. Daniel, do you have a question? Oh, yes, you do. Okay.
I'm curious if you've thought about how, like, I have an intuition that this sort of corresponds to Scholomizing with the relation between universals and existentials at different orders, and how that's precise. Have you thought if there's any correlation there?
Oh, the question is whether I've thought of whether there is a correlation between this and Scholomization, that is the relationship between existential and universal quantifiers. The answer is I haven't thought of that. So, lots of other people have thought of that, and there definitely is an adjunction between existentials and universals. Yes, that is exactly, and it's in fact one of the canonical examples of this kind of relationship. So, yeah. Thank you very much.